the other one? Oh, I think it's the okay, here we go. We already know what a logarithmic curve looks like. The basic logarithmic curve, we already know that. We know that it has an asymptote at 0, right? You can't make the logarithm negative. And it goes up and out like this. That's what a logarithm looks like as long as A is positive. Because what happens if you put a negative out in front of that? What's going to happen? It's going to turn it upside down. So as long as A is positive, and as long as B is greater than 1. Now we're going to talk about what happens when things aren't positive and bigger than 1, but this is your basic logarithmic curve. Everybody okay with that? Wait, do I have my letters right? Yeah. Yeah. So as long as A is positive and B is bigger than 1, that's what it looks like. Now, what if, we just talked about it, what if we have A less than 0? Still have an asymptote at 0, but now we have flipped it so it looks like this. Would you agree with that? So that is the exact same curve. So A is negative, B is still bigger than 1. And there we go. Now, let's pause a second. We're going to talk about end behavior and all that, but I want to just pause for a second and put some numbers in here. So what if we were graphing y equals log base 4 of x? Would you agree that looks just like that? Now, what happens if it's y equals log base 1/4 of x? So what happens if my base is less than 1? Well, now think about what is the corresponding exponential for this? The corresponding exponential, Charlie?
4 to the y equals x.
4 to the y equals x, right? What would the corresponding exponential be for this? 1/4 to the y equals x, right? And what do we know about 1/4? Wouldn't this be like 4 to the negative y equals x? Isn't that what that, another way of writing that would be? So this picture is this equation. Everybody's in agreement. This picture, okay. Now what happens when we change the sign on y? When we change the sign on y, we reflect over the x-axis, right? So if you took this picture and reflected it over the x-axis, wouldn't you get that picture? So making, okay, B is going to be positive always, okay? B has to be a positive number, but it can be less than 1. If it's less than 1, it has the same impact as changing the sign on y, which means it reflects it across the x-axis. So what if we had something like this? What if we had y equals -4 log base 1/3 of x? What's that gonna look like, Charlie?
Is he gonna flip over the y-axis, or is it? No, is that not?
Let's just think about it for a second. What does, forget this for a second. What did we just say that did? Making b less than 1 is like making the exponent negative, so that flips us across the x-axis. So this is already like this. Well, what happens when you put a negative out in front of that? It flips it again? Isn't that a double flip? So what's that gonna look like? That one right there. Okay. Stash all that up here somewhere. Celeste?
Is there an order like you have to look at it? Like you can look at the negative and
No. Okay, all right, so now we're gonna talk about end behavior of logarithms. So let's start with this picture. These are our two basic pictures. All right, so we're gonna start with this one. End behavior is a little tricky with logarithms because we are used to describing end behavior like this. This is the way we describe end behavior. What's the problem with a logarithm though? Can you do that? So the end behavior for a logarithm will be x approaches 0, right? From the right side. X is approaching 0 from the right side. Well, what's happening? As we approach 0 from the right side, we're going down. And as we approach infinity, we are going up. Does that make sense to everybody? So when I did this one, this picture, anything with this picture, as I approach 0, I'm going up. And as I approach infinity, I'm going down. All right, you and your partner try example 1. By the way, did we talk about my door decoration back there? On the outside, if you walk by the door, you'll see got all little math teachers, our little ornaments all around, but right in the middle, there's this guy's big head. That is Mr. Passwater, my hero. So that's his face right there. No one in the whole school gets it except the AP pre-calculus kids, but we all know Mr. Passwater. Practice writing your limit notation, guys. Make sure you're doing it correctly.
How do you do this then?
Remember with the logarithm, you're approaching 0 on the right side. The left side of the picture.
oh yeah.
This is the left side of the curve. That's the right side of the curve. Now for G, think about what that looks like. Your base is bigger than 1, so it's a normal logarithm. Your coefficient is positive. So isn't picture C, this first one right here? Normal logarithms have a base bigger than 1. When you make the base less than 1, that's when you have to flip it. This has a base of 3, so it's normal, it's positive. So your answer to C should be exactly the same as your answer to A. Would everyone agree with that? vocabulary from unit 1. Look at picture A. Are we concave up or down? Up. Are we increasing or decreasing? Decreasing. How about B? Concave down and increasing. Now C, you have to draw yourself, so stop and think. The base is bigger than 1, so it's normal. The 4 is negative, however, so it's going to take the normal and turn it upside down. So this is what C is going to look like. Does that make sense to everyone? Check that base first. I know I told Celeste or somebody it didn't matter, but I always base everything on the base. If the base is bigger than 1, that means it's normal in my mind. It has a negative coefficient, so that's going to turn it upside down. So that picture is concave up and decreasing. All right, example 3, we have some tables. What is the rule for a table of values in a logarithmic function? What are the x's doing? If it's a logarithmic, x's are exponential, they're multiplying, right? And then the y's are adding. Remember that? So you should have no trouble, the y's are clearly adding. You should have no trouble figuring out what k is in that first table. What is your k value in that first table? 4. Because you're timesing by 2? All right, go ahead and do the other 3 tables and let's share answers. All right, what'd you get for the second one, the second chart? What do you think k is there?
2.
2, right? Because we're going from 2 to 6, we're multiplying by 3, right? And from 2 to 6, we're growing by 4, 6 to 18, we're growing by 12, 18 to 54, we're growing by 36. All right, so what's happening in the next one, number 3? What'd you get there, Charlie? You got 11. Because what did you notice, Charlie?
I noticed that it's like 4 to 5 is 1, 5 is 7.
Growing by 1, okay, and then it's growing by,
4.
well, from 5 to 7 is
2.
2.
Sorry.
And you know it has to be growing multiplicatively. So to get from 1 to 2, you times by 2. So the next one has to be times 2 again, has to be the same number. So that means times 4, which means that's going to be 11. And then the next one would be times 8, and that would be 19. And what about the last one? E to the 4th. E to the 4th. All right, number 4, we're gonna find the domain and range of the following functions. I would suggest a graph, but you don't have to have one. But take a second, figure out the domain and range. I'm gonna have you come up and put them on the board. In example 4. Take a look at your picture if you want to draw one.
So, is this, wait, is this how much? 0 is the lowest. And like this whole thing is previous. And so, 3 right there.
Wait, isn't it already at, okay, that's that too. So, wait, right here, would it usually be on one? Like for normal? Letter B, 1, 0. And then you move it over to B4. Then it goes.
Range is negative.
How do you do the last one?
I'm doing maybe or
That one makes sense.
That's why it would be 3, 0, 3, infinity, but 3, 0, 4.
yeah, I need one more. I need one other. I have a jack card. Card? Actually, yes. I did some freshman. It was like a card. Ceramics? Was that like pottery?
As you're writing your domains, you're being careful. Asymptotes aren't included, so you should be using parentheses, right, for your numbers, because, you're gonna have that asymptote. I agree with everything that's up there. Does anybody have a question about that, Charlie?
I guess that it's negative 3 halves, but how is that even possible? Because I thought you couldn't have one negative.
You can't take the logarithm of the negative, you mean?
Yeah.
Okay, well, look at your equation. If you pick a number, let's say -1, when I put -1 into the parentheses, isn't it still a positive? As long as I pick a number bigger than -3 halves, that parentheses will stay positive. And that's the key. X doesn't have to be positive. The thing I'm logging has to be positive. Okay? Anybody else? We give it, yep, Leo?
So will the range always be negative infinity?
For a logarithmic curve, what do you think? Unless you've done something funky, like put it in absolute value or something like that, yes. Because, Leo, think about an exponential. What is the domain of an exponential?
From negative.
All real numbers and their inverses. So yeah, the domain is all real for an exponential, the range will be all real for a logarithm, yeah.
Will the graph always be on the right side of the asymptote?
Well, as long as we don't change the sign on x, because changing the sign on x causes a reflection across the y-axis. But normally, yes. But you can make your graph do anything you want by sticking on negatives and numbers and stuff, but yes, normally. Okay, next page, lumberjack graphs. The table below represents y equals log base 2 of x. So go ahead and plot those points on your little grid there. So just take, don't be confused by all the words, just take the points from the chart and plot them. So are you getting exactly what you would think you would get from that, plotting those points? What value of x would produce an output of -5? So think of your T-chart. You want y to be -5. What do you think that would be? What? 1 over 32. Why is that? Well, look at your equation again, guys. Y equals log base 2 of x. Doesn't that say 2 to the y equals x? And if y is -5, x would have to be 1/32, 2 to the -5. Okay? Most of us don't think in logarithm, but all of us can think in exponent. So if you're not sure how to interpret the logarithm, loop-de-loo it, change it into an exponent, and then it will maybe be more clear to you. All right, what's the domain and range of your function? Domain is 0, 1, and range is all of it. Number 3 we've already talked about, it's the inverse. All right, number 4. The graphs of 3 parent log functions are shown below. What do all of these graphs have in common? Well, what are some things they all have in common? They all contain the point 1, 0, which makes perfectly good sense because I don't know what their base is, but b to the y equals 0, or no, b to the y equals x, sorry about that, b to the y equals x. If you put a 0 in for y, wouldn't you get a 1 for x no matter what? Yeah. What else do they have in common? Charlie?
They're all logarithms.
They're all logarithms, absolutely. They're all increasing, they're all concave down. Now, you gotta tell them apart. One of them is log x, one of them is base 4, and one of them is ln x. Any thoughts? Can you figure it out? Charlie?
I think y equals log of x is the one that goes the highest.
So you say that Charlie's, what do you say, hypothesis is that this one is log x. Okay, what's the next one, Charlie?
I think the next one is going to be log 4 of x.
Okay. It's the bottom one, ln x.
Yep, that's
why you decided that.
Well, I know that y equals log of x is equal to 10 to the y equals x. And so I assume that when we plug in like an x value for that equation, we're going to get a pretty high y value. Right? Or wait, shoot, I messed up. My bad. Never mind.
Okay, so let's think about, I see what you're doing here, Charlie, but you might have it backwards.
Yeah.
So this one is 10 to the y equals x. This one is 4 to the y, and this one is e to the y. Now, if we give all of these the same y value, so e to the first, 4 to the first, 10 to the first. So if they have all the same y values, so the same height, which x value will be the biggest? Well, this would be the point, if y is 1, wouldn't this be the point 10, 1? And this would be the point 4, 1? And this would be the point e1? Well, let's see. E is 3, right? So this would be the point 3, 1. This would be the point 4, 1. And this would be the point, well, that's not right, I'm doing it backwards.
Or, yeah.
Yeah, this is the point E, comma 1, put right here. And then where would, so E comma 1 is right here. 4 comma 1 would be a little bit past it. And then 10 comma 1 would be clear out here. So when I connect, they all have that dot. So when I connect these, this one, isn't that the way they come out?
Yeah. Yep.
Now, Charlie, what you were thinking about was 10 is bigger,
Yeah.
and that's true. So if it were an exponential, 10 to the y is bigger than e to the y is bigger than 4 to the y. But we're doing the inverse of that. Does that make sense to you? All right, we've already talked about, if we shift it 4 units or 3 units to the right, you know what that happens. All right, check your understanding. You and your partner, let's do the back side of this. Let's get our thoughts up on the board when you're ready. Do not use a calculator for any of this. Do not use a calculator for any of it, okay? Celeste, problem number 1, did you notice something about it? Yeah. So you know what that does, change the sign on X, that does something.
not what it said.
For number 2, if you're that far yet, Parker says in order, the equations D, C, A, B, E. You gonna match that? Y'all good? No issues? Perfect. Where's the vertical asymptote in number 1? X equals 0, that hasn't changed, right? The asymptote of a logarithm is always gonna be at 0 unless you do what? X plus 5 or something, so it's at 0. The x-intercept for a normal logarithm, it's gonna look like this. This is a normal one, and the x-intercept is at 1, 0. So because we've reflected this one, our intercept is at negative 1, 0. Remember from a long time ago, changing the sign on x reflects you across the y-axis. So this guy is your picture, and there is your x-intercept. What's your domain? Negative infinity to 0. And then your range is everything. Charlie?
Wait, how does that work? How do you? Oh, I'm sorry, I was. So,
Do you have a question or not?
I'm just wondering how you get there. That's all. Like, is it because all the x values are going to be negative then? Is that right?
Changing the sign on x reflects you across the y-axis. So all the points that were on the right are now on the left. All right, and the last one, write an equation for a logarithmic function that has a vertical asymptote at 5. Okay, let's just stop right there. If the vertical asymptote is at 5, what do we know? X minus 5. Right? Now, we have to contain the point 11, 1. So in other words, I don't know what my base is, but if I put in an 11 for x, I have to get 1. Agreed? So 1 equals the log base b of 6. What does b have to be? 6. So your equation is that right there. All right, so 211 will be due on Thursday. I want to start 212 so that we have maximum exam time. So we're going to start 212. It's really easy. It's your properties of logarithms. So let's just skip straight to the example and see how much you remember. This is 212, example 1. For each of the following, condense into a single logarithm. Anybody remember the rule? How do we put these two guys together?
Don't you like take the x and you put it in front of it?
No.
Right?
No. If I want to write, I'm condensing this. Now, are there times when I put things in front? Yes, Charlie, but this is not one of them. If the logarithms are added, then the numbers themselves have been multiplied. This should make sense to you. What happens when two numbers are multiplied? Their exponents are added. this is the inverse relationship. When the logarithms are added, the numbers are multiplied. So your job was to take these two and put them together into one. Since that's a plus, they're going to go together as a times. Now look at B. B is the same directions. We have to write one logarithm. But this time they are being subtracted. So guess what I'm going to do? Divide. So it's going to be 5 over Z. The base is irrelevant. So that could be a 4, a 10, any kind of base, as long as it's the same. It has to be the same throughout the whole problem. All right, what about C? This is going to be 1 logarithm. Okay, do something with the x, the 5, and the z. What do you think? X over 5z. I think she's exactly right. Do you? You might say, well, wait, those are being multiplied, but what you have is this, right? And yes, those are being added. But you see what happens with the negative? It's going to distribute to both of them. So she's right. She's exactly right. All right. Now, Charlie, look at letter D. What is different about letter D?
This one, okay. It's got a 3 in front.
Got a 3 in front. And a number in front is the exponent. That's the property you were thinking of. So this is the log base 2 of x cubed minus the log base 2 of y. So step 1, just like PEMDAS, order of operations, take care of your exponent first. So 3 comes out here, it's that x cubed. And then when I put them together, it's going to be log base 2 of what? How are those going to go together? X cubed over y. Very good. Very good. X cubed over y is a division problem. All right, you try E and F. F's a little tricky, but I think you can figure it out. Yeah, Leo picked up that up above in the boxes, his example, that should be a minus, log base 3 of y minus log base 3 of y. All right, what did you think about the first one? Did you get it all put together? What did you put here in your parentheses? I need someone to tell me. A squared over 4b to the fifth. 4 4a squared over b5? Is that what you had? Now, here's the thing you have to be careful of, Lori. Could I change the order of this problem and make it look like this? Would that be the same as the original problem? And now can you see that 4 is actually a multiplier? If it had been a minus, then that would be this, because that minus puts it in the denominator. That minus is like a -1, and so when it becomes that exponent, it moves it to the bottom. But if it's a plus, it stands on it. So yes, I think Sam is right. Does that look okay to everybody? What'd you do with that last one? That's kind of tricky. Whoa.
I got log v6 of 36x.
I see some nods, Will. I think there's some people who agree with you, and then I think there's some people that are totally lost. Isn't 2 the log base 6 of 6 squared? Any number can be rewritten as a logarithm. So in this case, I need base 6 to match the whole problem. So 2 is the log base 6 of 6 squared. That's where you have the 36. If it had been a 3, it would be the log base 6 of 6 cubed. Okay, all right. Last one, example 2. What do you think? A, B, C, or D? Anybody got a thought? C. Audra says C. She right? She is. All right, good work. Tomorrow, seniors, we are going to finish this section and then start exam reviewing. So you'll need to watch the video, catch up the notes, and then see what we did in terms of exam review.